Welcome to the Computer Graphics class. In this video I want to give an overview and discuss what computer graphics is about, what we are going to learn and why we are going to learn this subject. Computer graphics is everywhere, so you must have met this field of science, probably as an application or as a tool. As far as applications are concerned, everybody played with computer games, which are happening in virtual worlds with which you can interact. Interaction may include killing enemies or achieving certain goals. Or you might use visualization tools to check or examine complex objects like aeroplanes. There are different types of visualizations. Visualization can be photorealistic, where the resulting image should be indistinguishable from real photographs. Or the result can be artistic, or using computer graphics terminology, non-photorealistic, which mimics the techniques and the tools of an artist who would depict the modeled scene. Computer graphics is not only visualization, it's also simulation, because we have a virtual world that should work, providing real-world experience. For example, we have to simulate fluids and other natural phenomena. We have to deal with photon transport, including light transport or high-energy particle transport. Photon transport is important in rendering as well. Higher energy photons play an important role in medical imaging or medical visualization as well. Computer graphics needs modeling as well, because in order to populate a virtual world with objects, we have to design or model these objects. Modeling operations require the determination and the definition of the geometry. This geometry can be the result of an interaction process between the modeler and the modeling tool, or it can be the result of some measuring process. For example, this image presents a three-dimensional world obtained with the fusion of depth camera measurements. On the other hand, computer graphics is a collection of technologies, including hardware and software technologies. Concerning hardware, probably everybody has met virtual reality displays and equipment or cameras allowing sophisticated interaction with the virtual world, and everybody has a powerful GPU card in his or her computer that is responsible for the rendering. Rendering is a computational intensive task, so it's not surprising that our graphics card or GPU is a supercomputer. In addition to these hardware elements, there is a huge collection of software tools. Some of the software tools allow us to access the graphics hardware. For example, we have low-level libraries or so-called APIs that can control the GPU. These APIs include the opengl. For us, this is going to be the rendering software. Or Direct3D is also quite popular. Vulkan, Metal are the other competitors in this arena. Unlike Metal or Direct3D, OpenGL and Vulkan are vendor and operating system independent. In addition to these rendering APIs, there are general purpose APIs as well, so they are not restricted to graphics applications but can exploit the huge computational power of GPUs. These general purpose APIs include CUDA and OpenCL as well. When we use CUDA or OpenCL, we cannot access the rendering-specific hardware of the GPU, including hardware elements like rasterization or clipping or alpha blending or Z-buffering, whatever. But we can quite flexibly program the programmable processors of the GPU. The very high computational performance of the GPU is provided by the large number of parallel processors, and these are available in CUDA and in OpenCL as well. Based on these low-level libraries, there are higher-level special tools as well. For example, game engines. Unity 3D is a good example for that, or modeling or animation tools like Maya or 3D Studio Max, or photorealistic renderers like LuxRender. I mentioned that in computer graphics we need not only rendering but also physical simulation, so there are libraries for physical simulation as well. Bolid is one example for that. And I also listed here PowerPoint because these slides are made with PowerPoint. And in fact, PowerPoint is also a rather simple 2D rendering and animation tool. As there are so many different software tools to do computer graphics, the main question is what we are going to learn in this subject. This is a word cloud from this paper, and the authors of this paper surveyed very many introductory computer graphics courses all over the world. And the result of their research is this word cloud describing the subject itself. It's worth locating first the technologies, because there is a frequent misunderstanding about informatics in general and in computer graphics. Many people think that informatics is nothing but programming, and similarly, computer graphics is nothing but the programming of graphics APIs or using tools like Unity 3D. This is not true at all. As you realize, here in this point cloud we can find only OpenGL and GLSL, which stands for OpenGL Shading Language, and we are going to use GLSL to program the processors of the GPU. But all the other terms in this word cloud belong to mathematics, physics, and algorithm theory, and these are needed to develop meaningful graphics programs. So we will learn this so-called theoretical basis in this computer graphics class, and we will exploit this theoretical basis in particular applications which will be programmed in the OpenGL framework using GLSL as well. But one thing is for sure, computer graphics is not equal to programming. Why do we use OpenGL if there are other alternatives as well? Well, I listed a few facts that must be taken into account when such a decision is made. We need a graphics library with which we can control the GPU. So the abstraction level of the graphics library must be above the GPU, and the graphics library should allow all GPU features to be accessed. It's a good thing if our graphics library is independent of the windowing or operating system. Therefore, our programs will be able to run on any equipment, including mobile devices as well. It's worth studying a software tool which is stable, which has a large code base and a certain future. So we can predict with pretty high probability that in 5 years the graphics library will still be around. To begin with, we need a general purpose tool which can be used for any graphics application. Not something very special, designed for particular small problems. The software tool should be simple enough even for beginners. Otherwise, computer graphics would be too frightening to start with. Finally, we are learning computer graphics right now, so we should get acquainted with the GPU hardware and the GPU pipeline as well. So it's an important point that the graphics library reveals the internal operation of the GPU at least on some level, and doesn't hide the internal things, because in that case we wouldn't be able to learn how the GPU works. Considering these facts, the only candidate is the OpenGL, together with its shading language or GPU programming language called GLSL. The subject is partitioned into chapters, and these chapters are needed to have an overview of computer graphics and to be able to develop nice graphics applications with OpenGL. The first chapter will be about geometries and algebras. We will start with the well-known Euclidean geometry, but I will also talk about non-Euclidean geometries as well, like the spherical or hyperbolic geometries. In computer graphics and in programming in general, we have to get the computer to do the job instead of ourselves. Therefore, we have to translate all information into numbers because a computer cannot do anything else but to add, multiply, divide, and so on numbers. So we will use that branch of geometry which is based on numbers, and this is called analytic geometry. To support our analytic geometry approach, our first class in C++ will be a so-called vec4 class that can represent 4-element vectors. And such 4-element vectors will be good for us to represent points in the three-dimensional space, vectors, planes, and quaternions, which are the four-dimensional generalizations of complex numbers, and we use quaternions to rotate in an elegant way. In computer graphics, we often have to compute the derivatives of functions. Instead of doing it on a paper, I will tell you how to do it automatically in a C++ program, and this is going to be the subsection of automatic derivation. In order to do that, we will use dual numbers, which are close relatives of complex numbers. Even in this introductory part, I will show you applications. For example, to have a feeling of spherical geometry, we will implement a route planner for airplanes. In hyperbolic geometry, we will see the incredible flexibility to tessellate the hyperbolic plane with the regular polygons. We will also visit the projective plane, where infinity is included. In fact, in this image, infinity is here, this purple line, and we can even see beyond infinity. The second chapter will target modeling, especially geometric modeling, where we specify points with coordinate systems and one-dimensional objects called curves and higher-dimensional objects called surfaces. As we use the analytic version of geometries, curves will be one-variate functions and surfaces two-variate functions. The real challenge here is to specify curves and surfaces for which there is no well-known analytic expression. Such curves and surfaces are called free-form surfaces, so our tools should be flexible enough to design dolphins and human hearts as well. The virtual worlds contain objects that are moving. Movement is a kind of transformation, so transformation is going to be an important topic for us. In addition to movements, transformations are also needed to change the coordinate system. For example, the virtual world is in its own coordinate system called world coordinates, while the image is expected to be rendered on the display, which has its own coordinate system. So rendering is nothing but the transformation from a coordinate system called the world coordinates to the coordinate system of the display. These transformations will be matrix multiplications for us. Even in Euclidean geometry, when we will deal with affine transformations that map lines to lines and preserve parallel lines, examples are translation, rotation, scaling, shearing, and so on. We also transform objects in projective geometry. Here, instead of Cartesian coordinates, we will apply homogeneous coordinates to identify points. In addition to vectors and matrices, complex numbers and their 4D generalizations called quaternions can also play a role here. Quaternion is just a tool to rotate objects around arbitrary axes. Having established the virtual world, we have to render it, which means a photographing process, and this photographing process produces an image on our computer screen. Rendering connects objects in the virtual world to pixels on the screen. There are basically two ways to establish this connection. We can start from the pixels. In this case, we talk of pixel-driven rendering, or we can start the process at the objects, taking them one by one when the rendering method is called object-driven rendering. Object-driven rendering is more powerful, and it is supported by the GPU, and it defines the rendering process as a sequence of operations like approximation of curves with line segments, removing those line segment parts which are outside of the visible region, and finally identifying those pixels that may belong to that particular line segment. This last step is called rasterization. For the algorithm of rasterization, we will exploit an ancient technique developed at the dawn of mechanical computing. With this theory, we are ready to start programming. We have to get acquainted with the graphics hardware and the corresponding software elements in OpenGL and GLSL. In addition to OpenGL and GLSL, we use GLOT to interface with the operating system, and we will use Glue to manage the different OpenGL versions. Learning the basic features of GPUs and OpenGL, we develop a few simple applications. Our first program will draw a single green triangle on the screen. Then we generalize it to render a painting of a famous painter called Victor Vasarely. We will add interactivity and animation in our third project when the virtual world contains a rotating and moving triangle and a polyline that can be interactively modified. We will apply our theoretical knowledge of free-form curve design and implement a software that can model these free-form curves. The real challenge and the really exciting stuff is 3D rendering. We start 3D rendering with studying the physics fundamentals needed to simulate the virtual world in this respect. We will introduce colors. What are they? How they can be specified by numbers? We will conclude that the radiance is the physical property that needs to be computed during the simulation in computer graphics, because radiance has a very important property. If two surfaces have the same radiance value, then the human eye will not be able to tell the difference independently of the distance or the orientation of the two surfaces. So if we set the pixel to the computed radiance, then the pixel will replace the illusion of the simulated 3D surface. For simulation, we are going to need material models like optically smooth surfaces, which can be transparent, and in that case it may refract light, or it can reflect light like a mirror. There are also rough materials which can be classified as fully diffuse or specular or glossy. It's also important to discuss the different compromise levels in physics simulation. For example, we can have a rendering algorithm or a simulation that deals with only single light surface interactions, and the resulting image is quite boring. Or we may have a fully physically plausible simulation taking care of multiple interreflections between optically smooth and also optically rough surfaces. Of course, the computational requirement of this so-called global illumination approach is much higher than the computational requirement of a simple so-called local illumination approach. Ray tracing is our first 3D rendering algorithm. It's simple, general, and beautifully elegant. This is nothing but a business card of Paul Hagbert that contains a full ray tracing implementation that is able to render spheres that can be mirror-like, refracting or diffuse type as well. Having acquainted with this algorithm, we will develop several applications. Here the spheres are optically rough. Here we also allow mirror-like or refracting surfaces, and the material properties can be different on different points, allowing textures to be visualized. Apart from ray tracing, the other important rendering approach is incremental rendering, which is also supported by the GPU incremental rendering pipeline. So we visit this pipeline again. Recall that we have already visited this pipeline with 2D rendering concepts, but now we extend our knowledge to consider also features needed by 3D rendering. So for example, we will learn how to approximate surfaces with triangle meshes in an aesthetic way. We discuss transformations and clipping in the three-dimensional world, and also visibility calculation that determines which surface may occlude other surfaces, and finally the shading that determines the color of different surfaces. A possible application, which is quite timely, is a simple game where an antibody hunts a virus, and if it can catch it, it kills it. For rendering, we consider both physically plausible rendering and artistic rendering as well, simulating an artist who would depict this scene. And finally, we will close this course with game development. I will introduce this space shooting game, which is like the vet's horse. It has all the possible diseases, so it's a suitable environment to demonstrate all features and algorithms of game development. I do hope that you are going to enjoy the course and you will learn a lot. Thanks for your attention.